let's do it. How can we help?
I have a question. I think I'm completely confused on like the entire idea of the inductive effect.
Okay.
If there's maybe like a way you could go over it.
Sure. So, let's take a look at a few carboxylic acids and take a look at induction. We'll make it really obvious. And let's just get rid of that methyl group. Okay, acetic acid versus trifluoroacetic acid. So we've got these two molecules. When we're talking about inductive effects, we're looking at the stability of the conjugate base, right? And we're looking at it in the context of being able to withdraw electron density. So in order for induction to happen, you need electronegative atoms nearby. A site of electron density. Because, as we hopefully remember from Intro Chem and Gen Chem, that when we have electronegative atoms, that by definition means they want to kind of take electrons for themselves within a covalent bond, right? They're going to make things polar as a result. And so if we compare these two molecules when they have lost their proton and they now have their negative charge, when we're just comparing them, they can both resonate. So resonance is not going to be a factor here. But we know that as we have these oxygens on that middle carbon there, the middle carbon being the carbonyl carbon, the one that has all those oxygens, when we're comparing these two carbons, both of them are delta positive, right? Because of these oxygens attached to that carbon. And so we have to think about ways to, when we're stabilizing a conjugate base, we want to think about ways to kind of disperse that negative as much as possible. And so one way to do that is resonance. So both of these can resonate between the two oxygens, making them pretty good. But we're going to see the molecule on the right, because it's got all these fluorines on there, and fluorine being extremely electronegative, all of those fluorines are going to be pulling electron density away from this carbon that they're on. And so we're going to be able to draw all our little dipoles of that purple carbon being now extra partially positive. That carbon there. There's too many arrows, right? Let's just avoid that. And as a result, if we now have this super delta positive purple carbon, it's going to start drawing electron density away from the carbonyl carbon, making this one actually now a little bit extra positive too. A little bit more so than we would normally expect a carbonyl carbon. And so as the electron density gets pulled away from that site of negativity, those oxygens with their extra electrons, that's going to overall stabilize the molecule. So the whole point of induction is it's kind of a minor way of being able to relieve some extra electron density around a center. So what this happens is these electronegative atoms, they will pull extra electron density through bonds away from the, let's see, how should we, let's just call it the negative. From the negative charge area. So let's see if we can't fit all this in here. So essentially those three fluorines are going to be kind of pulling electron density towards themselves, thereby relieving some of the concentrated electron density that we would normally see in acetic acid, or acetate, I guess, once it's been deprotonated. That electron density that's normally concentrated on those two oxygens is now being distributed more towards those fluorines, thereby stabilizing the molecule. And as a result, stronger acid.
Got it. And I know in your lecture you mentioned that there's other factors we should look at before looking at the induction effect. So we should look at the other factors before we go to the induction.
Correct.
Effect.
Induction should almost be your last step. So we can kind of follow the whole Cario thing. So cationic acids, again, these are only for apples to apples comparisons. It's my favorite thing to say. We can just do a quick blurb on all of these. How about we'll make protonated acetic acid versus regular acetic acid. Actually, although it's incorrect, we'll put the proton here just so we can have it compared. Obviously, if your acid is cationic, removing a proton makes it no longer positive. You're removing a charge. Whereas normally when we're removing a proton, we're adding a charge and we're adding a negative charge. And so we're going to see here clearly this one's the stronger acid, right? Not as common for us to see this, but it is a very important factor. Because everything else is the same, right? We're able to resonate and do all this other stuff, other fun things. But when it's you have the same molecule in a cationic form and it's already got an extra proton, it is a lot easier to remove that extra proton than other ones. So let's look at the rest. We have A for atom identity. That's going to be your biggest size atom. And there is, if they're of similar sizes, then we look at electronegativity. But typically, first we're going to look at size. If they're similar size, we look at electronegativity next as a secondary factor. For these are going to stabilize acids and make them stronger. So, for example, how about this one with the sulfur versus the oxygen versus the one with the nitrogen? If we're comparing these, oxygen, nitrogen, they're kind of similar size. Oxygen is a little bit smaller than nitrogen, but roughly similar size, right? Because they're in the same period of the periodic table. Sulfur, however, is a row down on the periodic table. It's below oxygen, and so it is the biggest size. That's our most important factor for the A portion of comparing acids. And so, as a result, we're going to say that sulfur is the biggest of our atoms to which the hydrogen is attached. And so it is going to make the most stable base, so therefore it is the strongest acid of these three. Now we're going to look between the oxygen and nitrogen. They have similar size, right? So we're comparing electronegativity. Between the two, oxygen versus nitrogen, which one's more electronegative?
Would it be oxygen?
Right. Remember, electronegativity is up and to the right on the periodic table, so oxygen is to the right of nitrogen, so it is more electronegative. It's more electronegative than nitrogen, so that is going to be stronger than that one. So first we want to look at the size. If there's one that is obviously a bigger atom, that means farther down on the periodic table, that one will win. And again, these are only when we're comparing similar things. And so you can see the only difference with these three is the atom identity, right? Everything else is the same. They have 2 carbons and the rest is all the same too. So if we were to rank these in order, the one with the sulfur would be strongest, then the one with the oxygen, and then the one with the nitrogen will be our third strongest, or our weakest, we could say. First came down to size, then it came down to electronegativity when things are within the same period. So resonance is our next one, and again, these are all the things you should look at before induction. So always look at these things first, and then only if things are identical in terms of atom identity and resonance, that's when we look at induction. But we can look at resonance too. R is for resonance. Here we go. Couple of things on the resonance side. When we look at resonance, the most important thing for resonance is, can it resonate? So if we're comparing two things, the first question is, can it resonate? If we're comparing ethanol versus acetic acid, of course acetic acid should be stronger, because once we make the negative, once we remove that proton, we have the ability to resonate the one on the left. Right? This can resonate onto the oxygen. No resonance. So, resonance always wins when we're talking about identical atom identity. So that's going to be your stronger acid, the one whose conjugate base is able to resonate. Because again, you're dispersing that negative charge. The tricky part is, what if both can resonate? Or what if multiple molecules can resonate? Multiple. What do we do then? Well,
would we then get the inductive effect?
I would not say that yet. I would say you should still be able, unless they're resonating exactly the same way, then of course, yes, we'll move to induction. But what if they resonate in different ways? I guess I should make that more clear, because as written, yes, this could be resonating the same way. And that point, yes, then you'd look at induction for sure. But let's say they resonate in different ways. So let's say we have these two molecules. No, this is a terrible example. Let's make it. No, this is terrible. Okay, let me choose another set of molecules that's not a carboxylic acid. Let's choose a yeah, we'll do this. Okay, so, sorry, I've got to put all my little lone pairs on and formal charges and all the fun stuff. There we go. Okay, let's compare these three. So, when we remove their protons, the atom is the same, right? They're all on oxygen, so we're allowed to now look at resonance. And so we can see, okay, we've got three molecules, they all have negatives on oxygens, atom identity is the same, we'll look at resonance next. Two of these molecules can resonate, one of them can't. So, we should be able to first off identify that this one will be the weakest, because it cannot resonate. Right, that one's no resonance there that it can do, so it's not going to be able to resonate that oxygen's negative charge away. And the other two can resonate, right? We can resonate to 3 different positions on the benzene, depending where we go. But the other one has a nitro group. And nitro groups are excellent places to throw resonance. And so if we want to go ahead and draw some of these resonance structures, should have chosen something more simple because we've got so many. But here we go. Let's resonate. If we do this, we can resonate onto a carbon. I'll go ahead and draw the resonance structure of this. We've got now our negative charge on that carbon. And the other two stay the same. If we are so inclined, we could resonate that negative to a couple of other positions. For example, I'll use a different color here. We can move that one and now move the lone pair onto a different carbon. Here, I'm going to flip the tablet here so we can kind of see all of them at once. There we go. And I'm not going to draw the third resonance form because it's the same as that middle one, but it's just on the opposite side. If we look at the middle molecule there, it can resonate in the same ways. I'm going to redraw these double bonds so that they're identical so we don't have to worry about rotating things. Okay, there we go. Let's go ahead and do that. Yes, we can resonate onto that same carbon as the other one has. Resonance structures always take so long to draw. But really what we're looking at here is which one can do better resonance. And that's going to make our difference in which one's going to be the strongest acid.
By better, do you mean which one can produce more resonance, or which one creates more, like, major?
I would say more the latter one, right? Because the ones with the on the left one, it can resonate 3 times, or resonate to 3 different positions. We're going to see that this middle molecule will be able to resonate also those same 3 positions, but it could also resonate onto the nitro, giving it not only an additional resonance form, but also actually one that is more important than these other 3. And let's go ahead and just draw that now. It's both of those. So you see that we can actually resonate this, and we're going to end up with a much more significant contributor than any of these that have a negative on carbon. Because we're going to end up now with an extra negative on oxygen that is next to a positive charge. So that's a great thing. Okay, one more structure. So we have our nitro group. Where are we? We have our benzene. We have our positive charge there. We have these negative charges here. And so we can see, yes, this one will have better resonance, and it will also have more. I would say more important is better resonance. I will write that down here. So as a result, because this middle molecule has better resonance forms, or at least one better resonance form than the molecule on the left, this one will be our strongest. And then that means that this one is the middle. So first question, can it resonate? If it can, it's better than something that can't. Again, assuming same atom identity. After that, we're comparing resonance. We're looking at first, which has better, meaning more stable / significant contributors. So that's our thing. And then if they have this relatively similar stability, then which simply has more contributors. So first look at the quality of the resonance, then you can look at how many there are. So a lot of this is very hierarchical. So first look at atom identity, then you can look at resonance. Within resonance, you're looking at which one's got better resonance. And then after that, which one has more resonance. So fun stuff. And then after all this, then you look at induction. So isn't this fun?
Thank you for explaining that.
Sure. And let me show you an example as well. We'll then look at induction. Let me see if I can spell induction here. Nope. There we go. followed by orbitals. So these, again, should be done in order. So let me switch screens here. Change windows. I want to show you some of these practice problems. So y'all can take a look. Okay. So if you go to Mrs. O's website, she has the most practice exams, and I remember modeling mine after hers. So I think the best one that I've looked at of the ones she's got keys available, which are only these two, the Fall 13 exam is going to be your most similar to mine. So when we're looking at acids, it would be something like this, where we are taking a couple of these compounds that are similar, right, in one way or another, and we're going to be, I guess she's got them as bases instead of acids, but mine will be on acids, because bases is just everything's the opposite, and I'm not going to throw that wrench at you, at least right now. So,
Professor,
yeah.
I can't see your screen. Are you trying to show it to us?
Did I not? Okay, let's see here. Okay. See, can you see the? Am I still showing Mrs. O's website?
I can't see anything. I don't know if anybody else can see anything.
Okay. Let me. What? Go ahead.
Yeah, I can see it.
Okay. So try double clicking my name again. That may be the difference here. And then let me know if you're able to see it.
I still can't see it, but
okay.
Okay. Which exam was it?
This is the Fall 13 one. Fall 2013. Exam 1. Also, Jolene, what you might want to do, you can also just try just disconnecting from voice real quick and then reconnecting. That may help it as well. So anyways, so I would say on this exam, question 1 is certainly a good one. This has the molecule with, identify all these bonding characteristics and, number of lone pairs and that sort of good stuff. Number 2, no. That's more her random things about citric acid and saliva and cocaine. Not really relevant here. Number 3, absolutely, would be a very important one. Resonance is probably the biggest part of this exam because, as we saw, it'll bleed into some of the acid stuff. So expect a molecule like this that will have multiple ways to resonate, and then being able to rank these in terms of which one is best, along with being able to justify why. So being able to explain why is the original molecule better than any of the resonance forms you've drawn, or whatever it may be. And answers may vary there, but I'll be looking at all of your work. Number 4, of course, is a good one. That would be, in our case, would be acids. I'm not going to throw bases at you. So you'll be comparing a couple of molecules using this Cario idea, where you're looking at these things in order of where the acidic hydrogens are attached. And you'll, of course, be asked to justify, meaning explain, your reasoning behind selecting that. And so for that, I do expect you to draw structures as appropriate. So, for example, if something can resonate, I need you to show me the resonance. If 2 things can resonate, show me why one resonance is better than the other. Or just draw the, conjugate bases and say, oh, well, this one's better because it's got a better atom to hold the negative charge, something like that. You'll have some naming stuff. So similar, although she's got a spirocycle, I don't think we cover those anymore, but you'll be expected to name stuff like that. You'll have some conformational analysis. This is not one that you'll see yet unless you've looked at next week's kind of first 2 videos, which I definitely recommend because you're doing this stuff in lab on Monday. And this will be on your first exam. So being able to look at these different projections of molecules and rotate them in different ways and identify the conformations as necessary. So something very similar to this. What do we have here? Something with torsional strain. Yeah, we can talk about that. The rest of these are for Chapter 5 stuff, except for number 9. Number 9 would be a good one as well. So 7 and 8 I would skip, because those are Chapter 5. We are not having that on our first exam. Number 9, yes. That is going to be important that we have these chair conformations and all of these little extra... no, those are reactions down here. We don't have those yet. Anything else here? No, the rest is all Chapter 5. So let's recap here. On this exam, good questions are number 1, number 3, number 4, although again I'm going to not do bases, number 5, number 6, number 7, the first number 7, that's curious, and number 9. By the way, I will not have nearly as many questions as she's got. Like, this is a little bit absurd, don't you think? For one exam, that's quite long.
Professor?
Yeah.
Do you have a lecture for IUPAC naming and nomenclature?
Yeah. Is it? Okay. I believe so. It should be this last one here.
Oh, okay. That's the one I haven't watched. Okay.
Okay, yeah. I hope so, at least. If I'm missing something, that's going to be a problem. Let's see. Okay, let's see some other... were there other exams? This is the key. So you'll have that as well. She's got the keys there, so you can see...
Professor,
yeah.
I didn't see the Monstera, the first problems on the answer key. So I'm not sure how...
Oh, you're right. Shall we do that now, then?
Okay.
We could, if you like.
Yeah, that would be helpful.
Okay.
And also, I was going to ask, do you have the answer key for the worksheet 2, the resonance and acids?
I should, yes. Although it would be helpful if one of you links it as well, just to make sure I have the same worksheet. If not, I can make a key for you.
Okay.
Cool. All right, so let's go ahead and do this first question here. So we can do it together. Although, as we know, these molecules, there's going to be a lot of drawing on them. So what I'm going to actually do is I'm going to go ahead and draw this on my tablet again, so we can just copy-paste it, save a little bit of time. And then we'll answer the questions as we go through it. So just give me 1 second to copy it. And then we have 102.
I noticed on one of her exams too, she had like a question about like enantiomers, diastereomers.
Not yet for us. That'll be on our next exam.
Okay.
Yes, because that's a whole nother monster, and I'm not going to throw that at you right away. Okay, so this is A. That's the oxygen. B is this random carbon. C is the nitrogen. And then D is this other nitrogen. Okay, so I'm going to switch the screen back to the tablet. Hopefully, Jolene, this will work for you. We'll see. Change windows. Okay. All right, so I have this molecule drawn now. And let me have it there so the recording can see. Okay. So, and I'm going to move the questions over here. So the first question is total number of sigma bonds. So, it's kind of hard to have us all go through this together, but sigma bonds, of course, are just single bonds, right? And anything that has a double bond also has one sigma bond. It's got one sigma and one pi. So the only thing that's going to be different here is that we're going to need to expand that nitro. The NO2 there is the only part that I would say is tricky on this first part of total number of sigma bonds. So remember that NO2 is really going to have the following. NO2 is drawn with a double bond to one oxygen and a single bond to another oxygen. And, we'll leave it like that. And that nitrogen is always positive as well. So, if we want to count the sigma bonds, we can just simply do that. I'm going to copy the molecule before we destroy it here. That is the advantage of tablets, right? We can do all this fun stuff. Okay. So let's draw each sigma bond as we go through and count them all. So I'm just going to go left to right as we do it. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh crap, we forgot all the hydrogens. Hold on. Pesky hydrogens. We were at 20, by the way, with that hydrogen, so I'm going to just indicate the rest of our hydrogens here as well. So don't forget, there are all these lovely hydrogens hiding out that we would not have thought about. Yes, that's correct. So that's the other tricky part, all this silly hydrogens. So we were at 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Am I missing any hydrogens? Yes, I am. There's 2 more. 1, 2. So what is this, 33 then, with that? I'm not so great at counting. But that's the trick there, is expanding any condensed groups, like a nitro group, and then putting in all the hydrogens that are invisible. So overall, in my counting of this, we got 33. Did anybody get anything different? Did I lose count while accidentally forgetting the hydrogens? Okay, hopefully so far so good. So, and then we want to draw implicit hydrogens as well. So those were the 2 kind of extra bits we had to do in order to count all the bonds on this. So don't forget about those. So anytime you have a condensed functional group like a nitro or something like a carboxylic acid, you'll want to draw it out. And you'll also want to include all the implicit hydrogens, meaning the ones that are normally invisible that we don't draw because these molecules look very monstrous with... Oh, you know what? I think there's 1 more hydrogen. I lied. There's 1 here. Alright. There we go. I was going to say there should not be an odd number, so this makes more sense. Okay. So all these pesky hydrogens are there. All our functional groups are expanded out. We have everything that we need, so we're going to have our bonds there. That was a more tedious question than I think any of the others. And so once you get that, though, once you have all your hydrogens out there, the rest will be a little bit easier to go through.
Excuse me, Professor.
Yeah, what's up?
Yeah, I have a question. In type of this question, if we miss 1 or 2 sigma bond, we get nothing.
Between which ones? I'm sorry?
I said in this type of question, counting question, for example, counting sigma bond or pi bond, if we miss 1 or 2 sigma bond or pi bond, we get nothing for
partial credit, of course. Partial credit, for sure. If you put 33 instead of 34, like, it's not going to be a 0. Absolutely. Yeah. Good point. Good question.
Thank you.
Yes, I think Mrs. O might be a little more rigid on that sort of thing, but I'm not. So, because I understand pesky hydrogens are a pain in the butt. But it is important that we, as we start getting towards some of our reactions, that we understand how many hydrogens are in each spot. So that's really the point of that question. All right, total number of non-bonding pairs. So what does that mean? What does non-bonding pairs mean? Oops. So non-bonding pairs are lone pairs. And since this question says non-bonding pairs, we're actually going to count the pairs. Beware if it's asked how many non-bonding electrons, then you'd have to double your pairs count, right? Because if you count, I don't know, 5 pairs, that's 10 electrons, right? So this question also says that lone pairs aren't shown, which is a little weird because on 2 of them they are shown. So we'll assume the rest of them have enough to make octets. So we're missing a lone pair on the oxygen. We're missing a lone pair on the bromine. Or rather, 3 lone pairs on the bromine. We're going to assume that chlorine and other nitrogen have already been drawn out the way they are in the original structure. So we'll leave those alone. So if we want to now count all the non-bonding pairs, which are lone pairs, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 total non-bonding pairs in this molecule. And just for the record, I'm going to just also indicate that that's 26 non-bonding electrons. Remember, 2 electrons per pair. This question asks for pairs, but if you're asked for non-bonding electrons, it means actually the number of electrons, not pairs. All right, does that one make sense? So again, we just kind of had to fill in the 2 that were not already filled. Again, assuming those are supposed to be. Since it says place all missing lone pairs in non-zero formal charges, and each atom should have a complete octet. So I guess does that mean the chlorine is, I mean, this is so vague, I'm sorry. This question is a little bit odd. Anyways, total number of sp3 hybridized heteroatoms. Let's copy our molecule again because it is now a giant mess. So let's have a fresh molecule to look at here. So how many sp3 heteroatoms do we have? This one I'll let you answer.
Professor,
yeah, what's up?
Real quick question.
Yeah.
For the Cl bond with that little, I guess what looks like a triangle stemming off of the carbon, does that indicate a double bond or is that a single bond?
So it's if you remember way back when we learned about like tetrahedral structures and 3D projections, that's what's called a wedge, and it means it's pointing out of the molecule. So for right now, for this exam, that does not matter. It's a normal single bond for us. It just technically means geometrically it's coming out towards you. And the opposite would be that dash that's like the hydrogen there. That means it's going into the, it's going away from you. So, but those are both single bonds, yes.
Okay. All right. Thank you.
Sure. All right. So who's got a count of sp3 hybridized heteroatoms? Anyone need help identifying what that means?
Is it just the bonds, single bonds with the non-hydrogen atom?
And non-carbon also, yeah. Correct. So it would be non-carbon, non-hydrogen atoms that have only single bonds. That's correct.
I count 3, but I'm not sure if I need to include the nitrogen that's on the other side of the oxygen.
The nitrogen, no, because the nitrogen has a double bond on it, meaning it's going to be sp2. So which are the 3?
The oxygen, well, both oxygens, the bromine and the chloride.
So that's 4.
Oh, okay.
Which is correct, it's 4. Heteroatoms that are sp3. So, right, we're looking at single bonded ones that, I mean, I don't know what's going on with this chlorine here, because I don't know if she intended for us to draw the extra lone pair there. If the lone pair is not there and there's only 2 lone pairs, it would actually be sp2. But let's not worry about that. Let's assume that she intended to have that lone pair there, because it's very strange to have a chlorine with a missing lone pair. So we'll just assume that it's supposed to be that way. I'm not going to throw any weird, completely bizarre things like that at you. All right, total number of non-zero formal charges. So I'll just give you a hint here. On the molecule, I've inadvertently already drawn in 2 of them. There's one more that we need to worry about. Actually, 2. 2 more formal charges on this molecule. Where are we going to find those?
The nitrogen and then the oxygen. Yeah.
Right. So, in fact, A and D, right?
A and D,
right.
yeah.
Right. So, this oxygen should have a positive charge because it's got 3 bonds. And again, we're going to assume that lone pair is there. And then the nitrogen on the right has 2 bonds and 2 lone pairs, giving it an overall negative charge. So we have, and then we have these other 2 from the nitro group. A nitro group always carries 2 formal charges, by the way. Unless there's some resonance happening. 1, 2, 3, 4. So we have 4 non-zero charges. All right, and those are in purple for us. All right, how about the electron geometry? What is the other G for? I think she misspelled EDG. Electron domain geometry. Rather than, and I don't even know what egg is for. Let's assume it's the electron domain geometry that she's asking. I believe that's just a typo. What's going to be the domain geometry? We have to remember back to our 101 material. Let me redraw our lone pairs. How do we figure out the electron domain geometry?
Is it based on the lone pairs and the groups, the surrounding groups?
Yeah. So how many things does bromine have on it?
4.
4 things, right? And therefore its geometry must be
Tetrahedral.
Tetrahedral, right. Because it's got 4 things. It is technically an AXE3, right? If we're looking at the bromine specifically, it has one outer thing, the carbon, the rest of the molecule, and it's got 3 lone pairs. It's going to follow the AXE3 pattern, which means it is tetrahedral. There are 4 domains on it. Anything with 4 domains has an electron geometry that's tetrahedral. So maybe useful to go ahead and look at that. All right, speaking of which, how many electron domains are on oxygen A? Let's copy the molecule down again. How many domains are on oxygen A? I'm going to redraw our lone pair that we already had there.
4.
4, you're right. Well done. 3 bonds, 1 lone pair. We could classify this as the following, if we were so inclined. 3 bonds, 1 lone pair, 4 things overall. All right, bond angle on carbon B. I will, because we've already got it elsewhere, I will draw in our hydrogen just so we can more clearly see that. In order to find out bond angle, we want to look at the geometry, right? And we can do that looking at the hybridization. We could do that looking at, I think the hybridization is the easiest way, but we can do this a number of different ways. So if we're looking at carbon B, which is this blue one right here, what's its geometry going to be? And then from there, what's its angle going to be?
Is it trigonal planar and
Yes.
then a 120 degree?
Absolutely, 120. It's trigonal planar, not 12. Let's try this again. 120. Because it's trigonal planar, it's sp2, right? It's got only 3 things on it. It's got this thing, and this thing. There are 3 things on it only. It's sp2. We could also say it's got 2 single bonds, 1 double bond. That's also sp2. And so as a result, it's going to have a 120 bond angle because of its trigonal planar geometry. Awesome. Molecular geometry on nitrogen D. That's our next question. So that's this nitrogen on the very right. Again, we can look at this through the lens of hybridization, or we can just simply look at the number of domains and assign geometry that way.
Is it bent?
So this is a curious one. If we're looking at here, let's replace this nitrogen or this. I'll say it's not bent. How about that? We'll leave it there. First off, how many? What's its electron geometry?
Trigonal planar.
Yes, it's trigonal planar electronically, right? So we essentially have the following. Remember I'm going to just put X as the rest of the stuff. Or I'll put R because we'll be a little bit more correct about it. When we're looking at molecular geometry, we pretend the lone pairs are not there anymore. So what's left? What does this look like?
Linear.
Linear, right. There's only 2 things, so it's got to be linear. I understand why you said bent, but we have to pretend neither set of lone pairs is there. So all we have is just a carbon double bonded to nitrogen, nothing else. Only 2 things that are atoms means it's linear.
Excuse me, Professor.
Yeah.
Can we say that because of the double bond fixes the molecule, so it should be linear?
Well, if it
fix the rotation of the molecule in 3D.
So it does fix the rotation, but if we were to put a hydrogen instead of a lone pair, then it is bent. So even though it's still got that rigidity from the double bond, this now is a some less than 120 degree bond angle that's going to be bent as a result. So it has to actually have both lone pairs there for it to have the linear geometry. Because this one with the hydrogen would still be bent even with that double bond. Right? Does that make sense?
I think.
Okay. Cool. A couple more here. We have amount of P character on chlorine. So again, we're going to assume that this lone pair should be there. So P character on chlorine. What the heck is P character? This is a little bit, I don't know, I feel like we don't usually ask this very much anymore. It's a little bit of an older type of question, but we can still do it. What does P character mean? I'm trying to remember if I even teach this anymore. Oh, one of you will simply say it if I haven't, right? So, P character on chlorine, what does that mean?
Excuse me, Professor. Is it the percentage of the p in hybrid
Correct.
orbitals?
Yes, it is. So what's the hybrid on the chlorine? Or what's the hybridization, rather?
sp3?
sp3, right. Which means that we have, of all of these letters, how many of them are P's?
75%?
75%, right. So it's 75% P character on that chlorine. Alright, and then the Vesper family on nitrogen C. What does she mean, Vesper family? Well, we can give a couple of answers, I guess, because depends what she actually means by that. So nitrogen C, let me actually move that down a little bit. Yeah, we can keep it here. Nitrogen C, what's its electron geometry? Oh, I know what she means by Vesper family. Vesper family is going to be the AXE type thing. What's its AXE notation going to be for nitrogen C? It has to start with A, right? How many outer atoms are on this nitrogen?
Two.
What about this one?
Oh.
So, what is it now?
3.
Yes.
So sp2.
For this, we're just, well, yes, it will be sp2, but for this, we're just asking the this AXE stuff. How many lone pairs are on that nitrogen?
None.
We're done. Ta-da! So that's simply it. Yes, it would be sp2. It would be trigonal planar, 120-degree bond angles, all that good stuff. But I believe what she's asking for with Vesper family is just this AX notation. Alrighty, let me see which others she does not have the key for. Okay, so she has number 3, 4. We can also look, by the way, at practice exam from fall 2019, the one that does have an answer key. Some of these will also be valid questions. Let me just identify those. I do have to take Gumbo to the vet in like 3 minutes. But the other ones that are missing a key, just let me know. Just shoot me a message, say, hey, can you do number 5 on this practice exam, and I'll post the key for you, or I'll write the answer, I guess. For if we just want to switch real quick to this, just so I can show the other exam that she's got a key for. Hopefully this doesn't kick Jolene off. We'll see. Okay, so we are on practice exam 1 from fall 2019. The first one, yes, good. Second one, no, we haven't talked about chirality yet. You can do the names of these bicyclics. Those are fun. We have one that's got acid and pKa order, which is great. So that's a good practice problem. I believe she has the key for this. I haven't looked at it. Again, if things are missing, let me know. 4, yes, good question. 5, yes, good question. Resonance and choosing stability. 6 would also be good question. Some conformational analysis here. Not number 7, though, because that is stereochemistry. So 1 through 6 should be doable, except for the first part of number 2. You don't have to worry about chirality yet. Okay, so I would take a look at those as well. Okay, and then yeah, I'll put up answers for the others that you've noticed are missing. Okay.
Okay, thank you. I'll send you through Discord the chat.
Perfect.
The worksheet too, and some of the other problems.
Awesome.
If you could do them. Okay,
Yeah.
Thanks.
Oh, I think I totally. I totally lost the screen on the other one. Oh well, that's okay. Charmos also has exams, by the way. Let's see. If we do this, we might see previous examinations. You've got some other stuff here with some keys. So there are more practice problems on that one. Okay. So take a look at those. I'm going to stop the recording now.